Well, hello everyone. Today I will try to delve a little bit into asynchronous procedure calls in Windows. Now, this is a somewhat obscure subject that recently came up in a conversation with my friend. Now, if you look at the documentation at MSDN, and this is, by the way, Microsoft specific stuff, you will get this little document that basically describes asynchronous procedure calls. And by the way, I will be calling them APC for short because I just don't want to like saying this whole thing. But the concept is really simple. Now, I'm not sure if this is Windows only type situation, but in this case, I will definitely be referring to Microsoft specific Windows code. Now, the way you can understand what asynchronous procedure calls are is by simply looking at a thread. Now, a thread, I'm assuming that you know what that is, basically like the primitive computing unit, in this case on Windows. It can execute some, well, let's say input-output procedure that normally takes longer than you would normally expect from a function. For instance, if you're reading from a file and the file is fairly large, the operation might take anything from a few seconds to actually minutes. Or if you have a timer that should fire, or if you're writing to a file. But pretty much a lot of input-output or I/O, it would be prudent to run as a synchronous procedure. Now, what does this mean? Well, you call a function, in this case, let's say reading from a file. You specify some initial parameters, what exactly you want to read, how much you want to read, where you want to read it from. And then you also specify what is known as I/O completion procedure, or a callback. So what the function does, it initiates the reading, usually done by hardware driver, and then returns. So it does so really, really quickly, so it doesn't really waste too much time. And because of this asynchronous callback situation, you can continue doing other things. And then when the operation completes, or if there is an error, the callback is actually called and you get your result. So in other words, when the process of reading the file was taking place, you were not waiting for it inside this function. So that's the kind of like nuts and bolts of asynchronous call. Well, Windows has this thing, which is a property of a thread, when it can associate an APC callback with that specific thread. Now, Windows has two types of APCs: kernel mode APC, which is a slightly different beast. It's implemented as an interrupt. So when it comes, the code is interrupted and the APC callback is executed immediately. Now, we will not be touching this type of APC because it's pretty straightforward. The one that we will look at would be user mode APC. And the reason I decided to record this blog post is because they are implemented in a really weird way. Now, queuing an APC, which is just basically setting a callback function, is fairly straightforward. What is not straightforward is how exactly the user mode APC is firing. Now, in this case, important part is to use some of these functions. What is not clear is how exactly you're supposed to call these things. And for me, for my experience in programming, I really did not use APCs that much. And in conversation with my friend that he brought up, he basically said, why? You can still use them. And as I started kind of going back in my memory, I remembered that I was really struggling to actually make the APC invoke the callback. And then I actually realized that these functions are the reason. Well, this is just a short paragraph that Microsoft dedicated to it, but indeed this is kind of tricky. So what I decided to do today, instead of just telling you all this stuff, just make a little app and just code it. So how about we do it right now? So I will fire up Visual Studio 2019 and we will create a project. It will be just a console app. It's a C++ one. And we're not going to go too fancy on it. We're just going to call test APC. Now I need to start off by saying that in this project I will be using C++ and I will be using Win APIs. So it will not be C++ standard, so please don't hold it against me. And the reason I'm not doing C++ standard is because this is absolutely Windows specific, and this is also Windows sysinternals in a sense. Okay, so that out of the way, we will need this windows.h header that will contain all of our Win API stuff. Okay, so now let's try to do what I just told you. And the first thing to do is to create a thread. Now I'm using Win API, which is the low-level way of creating a thread. Again, in C++ you wouldn't be doing this, but again, I will, for simplicity, I will just go this route. Okay, so we're not going to do anything fancy in this thread. So we don't pass any parameters, no creation flags, and we do not need any thread ID. Okay, so that's how we create a thread. If we create a thread, we get a handle. Okay, and if we get a handle, to be a good citizen, we need to make sure that it actually didn't fail. Now in this project I will implement very rudimentary error checks. Now in your production code you would definitely do something more substantial, like a logging function in here. In this case, what I'm doing, I'm just outputting an error and get last error code. Now the reason I do this is so that it's easy to debug this project, and the reason you would do this, or actually your real logging function in your production code, is so that you can track bugs. Okay, now since we have a handle here, to be a good citizen, so we have to actually close it when we don't need it. Okay, and one last thing, we need to provide this thread procedure. Now I usually don't keep all this stuff in mind, I don't memorize it, so I usually just search for it, then go to MSDN, where you can, by the way, read all the pithy details about this function. But what I need is this thread procedure. I usually just copy and paste it like so. Okay, and what we need to do, it has to return something, and at this point this should compile. Okay, what I want to do, I want to change it to 64-bit, and the reason I do so is because, well, 64-bit is the future. Now 32-bit is pretty old, so I try to always code in 64-bit if I can, especially test stuff. So let's compile it. And if we run it, well, absolutely nothing will happen. Well, because we just didn't output anything on the screen. So to make it interesting, or not interesting, but so that we can actually see what's going on, let's just output stuff on the screen. Now what I will do, I will output a thread ID so that we know which thread we're in, and then I'll just create, I don't know, just basic message, thread has started. Okay, and what we also need, because this thread will kind of loop through, not loop through, but go through really quickly and just finish. So to make sure that we can actually observe what is going on, let's create just some really long delay here. I'm just putting some arbitrary long number here, and then also put one over here so that we can delay the execution of our real program, of our main thread here. Okay, so if we run it, let's see what happens. In this case, we can see that our thread with this ID has been started. Well, cool, that's what we wanted to do. Well, at this point, just having a thread itself is not going to help us much, so let's queue an APC to that thread. Now let's see how can we do that. Well, if we go back, there's a function that's called queue user APC, which is quite appropriately called. So let's use it. So the first parameter is the actual callback, so we'll get its declaration a little bit later. The second parameter is the thread handle, which we have. And the third parameter is some arbitrary value. Well, in this case, we don't have it, so to make sure it works, let's just provide some 1, 2, 3 value. Okay, well, let's see what else is going on here. Okay, now the callback is very simple, so I'm just going to copy and paste it. It doesn't have to return anything. And we do this. Now, there are a couple things we need to do. First of all, just again to provide some output, we need to put a logging function, not logging, but the output function, so that we know which thread we're in. And also that the APC callback actually has fired. So let's just say that. Callback has fired with parameter. And let's specify this parameter. Now note that I'm using special ID specifier for printf because of the ulong pointer, which can be 32 or 64 bits. So it's not just %d, but ID to, match this. And let's see, we also need to check Q user APC for errors. Now, how do we do that? Well, let's check the documentation. As you can see, if it's succeeded, we'll return non-error. So, just for completeness, again, please make sure don't ignore errors. We need to specify this like so. Okay. Well, if you compile it and run, the first thing that will probably happen is that create thread by itself is also an asynchronous function. It queues the creation of a new thread into the kernel and then returns. Now, because we're calling Q user APC almost immediately, quite possibly that this API will also happen to run and finish queuing the APC callback before our thread even has a chance to execute. So this technically becomes a race condition because it might not happen quickly or it may happen quickly. Well, if you read through documentation here, again, I'm not going to scan through all of it, but it says somewhere that if APC callback is queued before the thread even had a chance to start, in this case, the APC callback will be called first before the thread procedure. To prevent this, we need to add a slight delay after our thread is created. Now, in a real program, you obviously would not be adding some artificial delay. In normal program, you would have code that will by itself create a delay. So again, artificially, we're just going to add a little bit of delay here. Okay, so right now everything is queued. We have all the notifications, and let's see what happens. We run our program, and our APC callback was not actually run. Now, what is the problem? If you put a breakpoint on Q user APC, as you can see, it fires, it goes through so the error doesn't happen, and then our program goes into sleep. But again, as you can see, the callback itself didn't fire. Now, what is the problem? Well, the problem are those magic functions that I showed to you. You see like this paragraph that says, hey, to be able to call, to invoke the callback, the thread has to call some of these functions. And that's what is usually confusing for people and was definitely confusing for me. So as you can see, our thread here doesn't do any of that. It just goes into a sleep mode, not sleep mode, into this just basically just dead weight. Well, to ensure that it can invoke an APC callback, we need to call sleepx. Now, please don't confuse sleep with sleepx. sleepx, if you bring it back, is one of those magic functions that has to be called to invoke an APC. Now, to do that, a thread has to be put into alertable state. That's what Microsoft calls it here. And to do it, we just have to provide true in here. Okay, so let's do it. Now, we need a really long pause here because we don't want it to expire. And then we need to put thread into an alertable state. And that's technically all we need to do. But before we actually run it, we have to again be good citizen and check the return value, because as you can see, there are two types of return values that can be returned. Well, let's just do that. So we get it here, and then, well, the easiest thing to do in our little test program is just to output it onto the screen. We can say sleepx returned, return this value. Okay, if we put semicolon here and actually compile it and run it, okay, voila. So as you can see, the thread has started, APC callback has been fired, and our sleepx returned value 192. Well, let's see, that's kind of interesting value. Well, if you look at the documentation, it has this wait IO completion constant that it may return, but we don't know what value it has. Well, easiest way is just to put it into the program and kind of like do the mouse over this value, and as you can see, it expands to C0. So let's just do C0. But what is C0? Well, if you bring our trusted calc and do C0, it is 192, right? So if we compile it and run it again, you can see that this value is exactly wait IO completion. So that's exactly what this API is expected to do. And again, if we get this simply from the return value of the sleepx function. Okay, so this basically shows us an easy way how you can invoke, how can you queue APC and invoke it in a thread. And again, the way the APC callback is invoked is from within this function or any of these functions that are named here. Now, I understand this is kind of frustrating in the sense that you have to call special function within a thread to be able to invoke the APC, but that's the way Microsoft coded it. Okay, well, this is really just nuts and bolts of how APC works. Right now, let's dig a little bit deeper into it. Now, the first question I would have is, how exactly does this work? Now, can I queue just one? What if I queue another one right after this first one? Would it like override it, or would it just queue them in sequence? Well, the best way to find out is just to do that. So if we do it in a loop, and instead of just doing 2, how about we do like 1,000 of them and see what happens? So we just have to modify it a little bit. Instead of passing a constant, let's just pass q in here so that we know which value was passed. And in case it fails, we can just say with q equals this value, not w, but q. And in this case, we need to break, because if it fails, there's no point in failing, the rest of the times. Okay, so this seems like we can queue quite a lot of them, but let's see if it works. So if we run it, well, voila, we just got 999 plus the first one, which was 0. So we got 1,000 APCs, callback functions that we just queued and that executed. That is really cool. Well, if you just leave this code as is, there's a little bit of a problem. And I can demonstrate this problem by introducing just a slight delay at the end of this loop. So again, what happens, we created a thread, and the thread started because we have this, very large delay. The thread started and it got into the sleepx function and kind of like hung up in there because we have an infinite delay and APC wasn't queued yet. But then, while still in this thread, we quickly looped, when this thing wasn't here, we quickly looped through 1,000 of these APIs, which by itself are really simple. It just adds this, this new APC call back into a thread and returns, and quickly went through like 1,000 of them. So what happens next is when this thread has its chance to run, inside the sleepx function, it sees that, hey, APCs were queued. And inside the sleepx, it literally executes all 1,000 of them, one after another, returns, we get wait IO completion, we print it, and then we go into this dead wait into the function itself. Well, if you think about this is another race condition that we created, because if you introduce delay, we will not get all 1,000 of them all at once. Let's take a look. All we get is just one. Now, why is that? Well, because of this delay, this little loop couldn't just like put all 1,000 of them while this thread was still sleeping for its time slice. Well, in this case, it was able to do just one. Then this thread woke up and had one APC, so it executed it, and then just moved on here. So, important part is that for every single APC that you queue, you have to also provide one of these functions or one of these to be able to process it. Now, to fix a little problem here, so what we need to do, we just need to create an infinite loop here. Now, in a normal thread, you wouldn't be doing this. You will always find some way to leave the infinite loop, but here it will work. And if we do it this way, if one of the APCs fires here, or a group of them, then we just simply get back to another sleepx, to another sleepx, to another sleepx. Okay, so now if we run it, in this case, as you can see, we were able to execute all 1,000 of them, one after another. So this is very important part to remember, again, that for every APC, we need to make sure that we have a recurring call to some kind of a waiting function, okay? Because if it's just one, you can easily create a race condition like I just showed it to you. Okay, so this is kind of tricky part about APCs. Okay, well, this part is kind of simple because, again, I'm using the console application and, well, it's easy. Let's see what happens when we get a GUI application. Well, let's create one. In this case, instead of doing the console app, we create the Windows desktop application, again using C++. And let's call it Test APC GUI without a better name for it. Okay, well, this time, again, I'm going to switch to 64-bit, and I'm going to compile it. Now, as you can see, this GUI app has a little bit of code here. So if we run it, so what we're going to get is just a basic, app that has like a dialog and has like menus, and you can exit it and that kind of stuff. Okay, well, let's see if we can queue APC into a GUI app. Well, technically it also has a thread, right? The main thread begins executing here. It's a single-threaded app because we didn't add any additional threads into it. Well, let's do it. So before we do that, I have to close some of these windows and open a resource view. Okay, since we have a GUI app, let me just save a couple steps, and I will create not REST but test APC menu item, and then let me go into properties and create a handler for it. Now the handler would be in a window procedure, which is registered here. Okay, so here you go. So if we add our handler here, and for that we need a function test APC. Well, you know what? Let's do it. Set test APC. And just for completeness, we will pass a window handle. So now we need to declare this function. It will be a void function. Now I'm not using any fancy ways of creating functions in Visual Studio, just to make it simple so that people can follow along. And what we need to do is provide the type, like so. Okay. And before we go any further, let's make sure that this compiles and that we can actually invoke our breakpoint. And here you go, it works. So what we just created is just a simple template that would allow us to test if we can queue an APC. Well, let's try it again. So we have our function, right? Queue user, if I can spell it, APC. Okay, we'll provide a prototype for a little bit later. Now in this case, we don't have a thread handle. Instead, we'll just use our own thread because it's a single-threaded application, and we can get to it by calling getCurrent thread. Here you go. And the value that we will pass is our window handle that we can use later. Okay. Now again, I don't remember how exactly the callback was declared. I know it's really simple, but I just want to go with what they have here in documentation. Okay, so I'm not going to declare it. It's really simple. And to make sure that we know that it was called, I'm going to invoke a message box. And it will be a very simple one. The message will be APC callback fired OK. And the title will be success. And this is message box icon information. Okay. Now before we go any further, we need to, H window, type H window, and we got it passed from this parameter here. Okay, so and then we need to specify the callback and also be good citizens and actually handle errors. Now to show that we have an error, we just do this little message box. It's basically for us so that we know that something went wrong. Now in production code, you obviously would be using a logging function. Okay, so let's see if this compiles. Okay, and it does, and let's see what happens. So again, here's our window. A breakpoint fired. Queue user APC worked fine, and nothing happened. Well, let me remove the breakpoint and try again, and nothing happened. Well, why is that? Well, the reason queue APC didn't queue, or queued, but the thread didn't invoke our callback is again the same problem as I showed you, is that none of these magic functions as I call them weren't called. Now this is a really a conundrum for me, why Microsoft didn't implement it, but they didn't. Now if you look at any GUI app, the most time that it spends in is a message loop. As you can see, the get message is the function that gets called, and it basically waits until any message arrives. So inside this get message is what technically should have been a an option to invoke APC, but, well, there is none. So how do we, go about it? Well, there is a way to address this, and it's fairly simple in this case. Now, to fix this, well, first of all, we need to go into a loop, like so. And in this case, we need to call a special function which Microsoft did not put on that list, but I know from my experience that it does the exact same thing. It's called message wait for multiple objects x. Now I know it's kind of a mouthful and looks pretty intimidating, but it's not. So let me show you what it is. So if you go into MSDN and look it up, you will see what it does. It basically waits for a bunch of handles. But the good thing about this function is that it can also wait not only for I/O completion, that's what we need, or basically for APC. It can also wait for a bunch of other things, like events, user input, basically all kinds of messages in the queue, which is exactly what we need. Okay. Now in this case, we don't need everything that this function provides. For instance, we don't have any handles, so we specify 0. Null pointer because we don't have any handles. Now the delay would be infinite. Okay, now wake mask is important, so let's look it up. And what we need is everything. Basically, we need all input. Now the reason we do this is because basically we need all kinds of messages, because pretty much any of these would be necessary, since they will be processed by get message. So we need all input, and then as a next parameter, obviously this is very important because we're waiting for an APC, we have to put our thread into alertable state, so that's what this flag does. And also we need to retrieve all the input with the message so that we can later process it with peak message. Okay. So here you go. Now again, we want to be good citizens. Please don't forget about this. We check for errors. And unsurprisingly, this function can return an error from especially that many parameters that it accepts. And sure enough, wait failed. That's what it will return. Now if we get here, the first thing we need to do is obviously break from our loop, and which is also important, we need to return special exit code. So let's do it here. In our case, we will return -1 because that basically tells us that there's a problem. We can probably put a comment here. And what we also need to do, which I kind of like doing, is to put some error checking here. Now in the GUI app, for the development stage, I like to use assert library. Now what assert library does, it has this very interesting macro that's called assert, and in our case it will be false. So what assert does, let me just show you real quick on a little tangent here. Now if you specify some parameter, let's say int v equals 1, you can check with assertion if v is indeed 1. So, and what this does, in a debugging build, it will see if this expression evaluates to true, and if it does, it won't do anything. And if it evaluates to false, it will show an assertion. But what's important is that when you build it as release, all of these checks will not be done. So it's kind of like development stage checks, which are really important. So let me show you what happens. So right now v is indeed 1, so it will just skip over it and nothing happened. But if you do v equals 2, this little check will evaluate to false, and when you run the app, you will get an assertion that says, hey, at line 37 in this file, exactly here, you have an assertion. And then you can just start debugging, which is very, very easy. I mean, very, very convenient. Okay, so in this case, what we're doing is if we failed, we will show assertion in every case in here. Okay, this is important again for debugging stage so that you can catch situations when something goes horribly wrong, like in this case, because technically that should never happen, that it will return fail. Okay, so that out of the way, we're obviously not done. So now what we need to do, we need to create a second loop, and in it call peak message. Now what peak message does, it literally retrieves, or peaks in this case, a message from the message loop. And the reason we know that it's here is because we specified this flag. Okay, so it's really simple. We don't need anything special here. The only thing we need to do is remove that message from the message queue. And this loop will continue on for as long as we have message in the queue. And if we don't, we go here and then we wait for either the APC callback or the message. Okay, so next is a little bit of a different way of processing messages versus this loop. Again, we're doing this because we're not calling getMessage, so we're kind of like unfolding it. We need to make sure that we catch a moment when the message quit is returned. And this will happen when the application is closing, and this is a normal exit. So what we do is that we return whatever W parameter was at the time from the message. Now, the reason I know this is if we go and look up WM quit, it tells you that this is the exit code that was specified in the function, so it's kind of like by convention that's what we need to return. Okay, well, and the rest of it is pretty much this stuff, which is pretty straightforward. We just do copy and paste. And let me remove the comment. Okay, so let's compile it. Just to make sure it works, let's put a breakpoint here and run it. Okay, so as you can see, our program is working fine. There's really no difference here. But let's see what happens when we try to invoke our APC. Well, here you go. It actually works. The callback goes through. Okay, so the last test is, let's see what happens when we close the program. And here you go. We got here, and our application exited. Okay, now I understand that this is kind of like a lot of code. Well, not a lot of code, but quite more code than what I had here. But this implementation with the use of this function is how you can convert just your regular message loop into something, into another message loop that will allow you to process APCs. Okay, well, you would think that's all nice and tender, but what about a dialog box? Now, if you look here, the way we created our window is with the use of create window, which is fine, but there is one problem here, and the problem is that create window gives us access to the actual message loop. What if we don't have access to a message loop? Well, let's see that situation. If we open our dialog window and, for instance, create, let's see if I can create a button, and let's just name our button not REST but test APC, and let's give it a name too. And just for completeness, we need to put a handler, and the handler will be in the about dialog, about window procedure for the dialog. And just to kind of do it quickly, wparam equals that. Okay, and let's see if I can invoke our APC from here. We need the window handle. It's that. Okay. Well, let's compile it. Again, bring our app here. Let's make sure that the old APC still works, and it does. Let's see if we can invoke it from the dialog. Okay, the function is called, but nothing happened. Okay, and here's the problem. And the problem is, if we look at where our window procedure came from, well, it came from dialog box. And dialog box, you know, if we go into peak function, it's actually a macro for dialog box param w. Now, if you look at that function on MSDN, you will realize that this is a modal dialog box. And the modal dialog box does not expose a message loop. So you can get window parameter, dialog procedure, but it does not expose the message loop. So what do we do here? Now, this situation is a little bit more complex, but it is still fixable. Requires a little bit of a hack, but we can still do it. Okay, so this one line is not going to work for us because, again, internally it calls getMessage, which we do not need. Let's try to write something that will actually give us a message loop. Now, how do we do that? Well, the obvious thing is to create a modeless dialog. And we create that with using create dialog. I know it's kind of like a similar function, but there is a big difference between them. Again, this one creates a modal dialog. This one is a modeless. Now, the contents of a call are still the same. There's no difference here. But the difference is that it will return a window handle. Again, we want to be good citizens and catch all the situations when we have a problem. Now, because we just created a window, we need to destroy that window. Okay, this is important. And just for completeness, you might want to do this so that you don't reuse this handle. Again, this probably is not going to help for the program, but it will help for debugging. And before we show, with the way the modeless dialog boxes work, or any windows work, we need to show them. Okay. Now, to make this work, we need to provide a message loop. Now, the way to do this, and to save time, we can use or reuse what we had here. So why don't we do that? Okay, so we have a, let me just split it up a little bit so you can see it. So we have a loop right here that we will call our message loop, but it's a special one. Okay, now this function is the reason why we are unfolding it. That's the whole reason why we're doing this. So it doesn't change a single bit. The only thing we need to change is that we need to remove this exit code. Now, if it fails by some reason, we just have to leave this loop, because otherwise, if it starts failing over and over, we'll be, using up a lot of CPU resources. What we need to do, we need to create our message variable so we can use it. Okay. Now, the peak message, again, stays the same. There is no difference here. But Now we'll get back to that a little bit later. What we need here is to process special dialog message, not just to process it, but to see if the message that we received is a special dialog message. Now the reason we want to do that is so that we can process the keyboard. In this case, the special dialog message should not be processed through these functions, so we have to create not. And now we can't use translate accelerators, but for simplicity, we're just going to check as such if we have our message that is a keyboard, key first and message. In other words, if it's between key first and key last, we translate accelerator because we don't need to do anything else. Otherwise, we dispatch the message. Okay? Now this would technically work, except there is one problem. We don't have an exit from this loop. Before, if you remember, we were waiting for wMessage quit. Well, wMessage quit is not going to be sent from the dialog procedure. So what we need to do is a little bit of a hack. Hack. And this hack comes from knowing how end dialog function works. Now, in any dialog procedure, you would be calling end dialog function to actually end it. Now, the end dialog is called only in a modal dialog box, and you would not be calling it in the modeless dialog box. In the modeless dialog box, you would be calling destroy window. Well, because in our case, the original function was written as modal, we have to adjust for end dialog. And just by looking at how end dialog works, we can do so. And what happens inside end dialog is that it sends a null message to our window. Now, to make sure that this is our window and not something else, we need to do this. Okay, and then when that happens, this is our normal exit from our main loop. Now, we can't use break because then the break would break from here. We need to break from the main loop. Now, there are several ways to do it. I will just do it this way through a function. And I will say while not this. And then I will set it to true and do the break. Okay, so let's see if this works. We need to compile it. Now the first test is just to make sure that we didn't break the message loop itself. Let's try it. If we run it, so you can see we can press buttons, and this is our end. Let's see if that works, and it does. Let me make sure that we can run it again, and sure enough. Now the problem that we have here is that we created a modeless dialog. Now what's the difference? Well, let me show you what's the difference. When you run it, the modal dialog will not allow you to create another dialog. But look at this. You can create another one, you can create another one. So that's not how this should work. So we need to create this as a modal one. So how do we do this? Well, it turns out it's actually pretty easy to do. And the way we do this, create as modal, we simply disable the parent window. And the parent window is this. That's all it needs to be done, because, okay, that's the parent window. And once we did this, the important thing is that at the end, after we destroyed our window, we need to enable the parent back. And that's all we need to do. So if we run it again, see if I try to go back, well, it won't let me. Well, let's see if our APCs work. And sure enough, they do. Okay, so this, I understand this definitely is way more code than just calling this, but this little procedure here basically does what this thing does, except it allows us to invoke asynchronous APCs. I admit that it has a little bit of a hack here. Ideally, what you would want to do, you would actually want to go into About Procedure, and instead of calling end dialog here, you would actually destroy the window. Instead of doing this, you would destroy this window, and then at that point you would have to catch Windows post and C destroy in the message loop. But this will involve rewriting existing procedures, which you might not want to do. So the easiest way is to just rely on this kind of hack, provided that inside your dialog message loop you do not call WM null. And if you control all of it, that should not be a problem. And again, let's make sure that it works. We can invoke APCs here. We can do it repeatedly. And we can also do it here in the dialog box. Okay, guys, so this will conclude our topic. This is kind of like a deep dive into Windows asynchronous procedure calls. And obviously this involves Windows APIs. So thank you for watching, and see you next time.